My name is Chaitanya, Physics faculty at Shakthi International School. Today, in this video, we are going to learn an important topic from class 12 chapter Moving Charges and Magnetism. Moving Charges and Magnetism. From this chapter, we are going to learn about Biot Savarat law, Biot Savarat's law, and application of it we will see. We know that whenever there is any current carrying conductor, if this is your current carrying conductor, due to the current carrying conductor, there will be a magnetic field generated around the wire in a circular loops. So now here, if you are understanding according to your right hand thumb rule, the magnetic field at this point will be going inside and the magnetic field at this point will be coming outside. So we are representing the direction of magnetic field and we represent that magnetic field as B. B is the notation symbol that we use for representing magnetic field. So you have learned this in your 10th class that magnetic field will be going inside and it will be coming outside at this regions. At point P it will be outside and at point Q it will be inside. And at any point if you are seeing, it will be tangential to this direction of your circular path. Okay. Now we know only the direction of it, but what about magnitude? Biot and Savarat has conducted different experiments to understand how this magnitude is actually changing. According to Biot-Savarat's law, the experimental derivation goes like this. If there is a current carrying conductor of length L, they cannot define the length total. They cannot define the magnetic field for total length. For a small dl length at a particular point, which is at a distance r from the dl length, okay, will be given as dB at this particular point. Now this dB is experimentally found to be directly proportional to the current. If the value of the current is increasing, then the magnetic field at that particular location is also increasing. How did they check this experimentally? The deflection in the compass that is kept at that point. For a smaller current is small, for a higher current is more. So giving you the relation between magnetic field at that particular point and the relation of current with it. In the same way, it is inversely proportional to the square of the distance between them. It is also directly proportional to the total length. It is also proportional to the sine of angle between sine theta, where theta is the angle between dl and r bar, where dl and r bar are vector notations of length and r distance. R bar is in this direction, dl bar is here in this direction. Okay. So the direction of magnetic field does have a direction. That direction of magnetic field will be given by cross product of dl cross r bar, dl bar cross r bar. Okay. So to be precise, when you are representing it as a formula, it will be giving you the final output like this. The dB can be written as proportional to I dl sine theta divided by r square. When we are removing this proportionality symbol, we have to introduce a constant, and that constant is going to be dB is equal to mu naught by 4 pi into I dl sine theta divided by r square. Now this is a scalar form of equation. Okay. In this case, what is the value of mu naught by 4 pi? Mu naught by 4 pi is a constant value. It is equal to 10 power minus 7. Okay, 10 power minus 7. If you can get the units from here, from the equation. Okay, magnetic field is Tesla meter square per meter into ampere. We will be writing it as Tesla meter per ampere. Okay, So that will be the units. But I'm concerned more about what is mu naught. Mu naught is called permeability. Permeability. Okay, epsilon naught you might have learned. Epsilon naught is called permittivity. Okay, the value of mu naught is 4 pi into 10 power minus 7 if you remember. Epsilon naught value as 8.85 into 10 power minus 12. Okay, so permeability is the ability of the medium to allow magnetic field lines. Ability of medium to allow magnetic field lines. Okay, permittivity is ability of the medium to oppose electric field lines. Electric field lines. Okay, so now coming to the equation, we have a final conclusion that dB is equal to mu naught by 4 pi into I dl sin theta divided by r square. If you are writing it in a vector form, dB can be written as dB bar is equal to mu naught by 4 pi into I dl sin theta divided by r square into r cap. We have to find what is this r cap. Okay, unit vector we have to take in that particular direction, and that r cap is the direction of dB. dB is actually going inside when the current is actually moving in upward direction. Okay, at this particular point the magnetic field is going inside. So this is the direction of dl, this is the direction of r bar, the magnetic field is in this direction, this is b bar. Okay, so doing this, understanding this relation, you know that if dl is rotated towards r bar, we have to write it as dl cross r bar using a screw rule. Okay, screw rule, that is your thumb or the fingers, okay, all the fingers of your right hand are to be placed in the direction of dl. So this is the direction of your fingers. Okay, now let me draw it again. So this is the direction of your right hand fingers, dl, which are representing dl. Okay, in a bar cross b bar, we always write a as a fingers direction and b towards in which the fingers has to be rotated. Now this is the direction in which fingers has to be rotated because this is the direction of magnetic field. It is like this. So you have your fingers in upward direction in the direction of dl. If it is being rotated towards the direction of r, the resultant output is coming inside. So that is the reason why you will take it as dl cross r bar. Okay, so dB bar is an output when you are doing it as dl cross r bar. Since all three are vectors, we have to do a cross product here. So finally, if you are writing in a vector form, instead of writing it as dl sin theta simply, we are going to write it as dl cross r bar. Okay, divided by r cube will be changing. Okay, without changing any equation here. In this case, if you are substituting dl cross r bar as dl into r into sin theta. Okay, since I have divided with r already, this r will be getting cancelled. So your final formula of it will be again remaining it as the same dl sin theta divided by r square, ideal sin theta divided by r square. So that's what you have to understand. So this is the equation given by Biot Savarat according to their experimental observations. Okay, so finally the magnetic field due to any particular point at any particular point due to the small current carrying conductor can be written as mu naught by 4 pi into I dl cross r bar divided by r cube. Okay, this is a vector form of it. This is your vector form of equation. Okay, now application of it. Let's say I am taking a current carrying conductor of length L at a distance r, let's say at a distance d. or A, let's say I am taking. At a distance A, I want you to find the magnetic field intensity due to this entire wire. So according to this thing, okay, since it is having it is a continuous wire, I am taking some dl length at a distance. Let's say from here to here at a distance x, I am choosing a small, or let's say at a distance L, I am choosing a small length dl. Okay, this is your small length dl. Now the current is passing in this direction. From here to here, I have to draw a line. Okay, let's say if I am taking this one as angle as theta, this angle can be written as 90 minus theta. So according to the formulas, okay, which is dB bar, the small dB at this point can be written as mu naught by 4 pi into I dl sin theta, where sin theta is the angle between dl and r bar. Here the angle between dl and r bar, this is your dl and this is the r bar, is 90 minus theta. So substituting that 90 minus theta, 90 minus theta, you will get the equation of it. Okay, divided by r square also is there. In a vector form we are not writing, in a scalar form let's say we are writing, will give you this equation as mu naught by 4 pi into I dl cos theta divided by r square. This is the general equation for any particular point due to the smallest length of that wire. But we want to analyze for the total wire. If I have to analyze for the total wire, this entire wire is having a length. Now to cover this entire length, thetas we have to analyze. I have to go in this direction to cover this side by an angle theta 1. I have to go in this direction to cover this side by an angle theta 2. And this is your clockwise direction and this is your anti-clockwise direction. Now, whenever we are having this sort of conditions, we have to take, since we have already taken, we have to integrate it to find the total length of it. Okay, so if you are integrating dB, you are going to get total magnetic field B. In the same way, if you are substituting those two formulas in this equation, okay, we are trying to analyze different parameters of it. Now we know this length from here to here is A. We are having a right angle triangle. This length from here to here is A. So now from that right angle triangle, we are writing some trigonometric functions. So this is your angle theta. This length from here to here is A and this length is L. From here, if I am writing tan theta as an expression and this distance is R, right? Where this is the distance we are substituting here as R. This is your R. Tan theta can be written as opposite by adjacent. What is opposite side? L divided by A. So can I write L is equal to A tan theta? Now, if let's say in this expression I am having dl length. So I want to differentiate this with respect to dl, with respect to theta. So dl by d theta can be written as A into secant square theta, because differentiation of d by d theta of tan theta is secant square theta. So using that, this dl by d theta as A secant square theta, and I can write dl is equal to A secant square theta into d theta. This is what I can write for dl length. Now from the same right angle triangle, I can write cos theta also. Cos theta is adjacent by hypotenuse. Adjacent is A, hypotenuse is R. Now secant theta can be written as from here R by A. So that implies secant square theta will be R square by A square. Now we are using these conditions to substitute in that. Okay. So now the general formula of dB, we are getting it as mu naught by 4 pi into I dl cos theta divided by r square. So now in place of dl and in place of r square, I can substitute A secant square theta. I can write r square as A square secant square theta. Substituting both in that condition, mu naught by 4 pi into I In place of dl, a secant square theta d theta into cos theta divided by r square plus a square secant square theta. So these two secant square gets cancelled. A and a is getting cancelled. The final value that we are getting dB is equal to mu naught by 4 pi into I cos theta d theta divided by a. Now, why we are actually bringing into this form? Because whenever we are integrating, we have to integrate only one variable, and we need a function with which we are actually integrating it with. So we cannot integrate cos theta and dl form. So we are bringing, by eliminating the remaining variable, the dl length, we are bringing it into the function where it is being integrated with the same function. So now, if you are integrating on both sides, integral dB is equal to mu naught by 4 pi into I by a are constants into integral of cos theta d theta. The limits are from minus theta 2 to theta 1. Why I am taking minus theta 2? Because to cover the entire length, I have to go in anti-clockwise direction with minus theta 2 and clockwise direction with the theta 1 angle, if you remember the initial explanation. Now, integrating it, we'll be getting mu naught by 4 pi into I by a. Integral of cos theta d theta is sin theta. So when we are substituting in terms of sin theta, the upper limit and lower limit, theta 1 minus theta 2, we can write this entire function as mu naught by 4 pi into I by a sin of theta 1 minus upper limit minus lower limit minus theta 2. Now, you know, sine of minus theta is nothing but minus sine theta. So if you are doing the same here, you will be ending up with mu naught by 4 pi into I by a sine theta 1 plus sine theta 2. So this is the general formula for finding magnetic field intensity due to any current carrying any current carrying wire. Let's say if it is an infinite current carrying conductor. Example, let's say this wire is stretching up to infinite length, okay, in both the directions. Then what is the magnetic field intensity formula we can ask at this particular point at a distance a. So now we have to understand theta 1 and theta 2 in this condition. So now as the length is increasing, the angle theta is continuously increasing. Since it is going at 90 degrees, I have to go, since it is going to infinite length, I have to go at 90 degrees in order to meet it. Because as the length of this wire is increasing, I have to, let's say till here it is a wire. If the length is increasing till here, I have to increase it further. In the same way, if it is a wire which is going up to infinite, I have to go at 90 degrees. So for a infinite wire, theta 1 and theta 2 angles are going to be 90. Substituting both the angles 90 in this expression will give out the value of B to be mu naught I by 2 pi by A. Mu naught I divided by 2 pi A. This will be the formula, because sin theta 1 plus sin theta 2, sin 90 value will be 1. 1 plus 1, 2 you will be substituting, 2 and 2 will be getting cancelled 2 times. So if let's say this is your infinite wire, infinite wire. For example, if they are asking for a semi-infinite wire, semi-infinite wire. For a semi-infinite wire, this is how you will be having. This is extending up to infinity. This is the point where we have to find. Now, to reach this infinite length, you have to go at an angle 90. And the theta 2 in the anti-clockwise direction is going to be 0 in this, because you are already at that same point. You are not going to move any angle. So now substituting that, you will be getting B is equal to mu naught I by 4 pi A. Substituting theta 1 and theta 2 in that equation will give you the magnetic field due to that semi-infinite wire. Using this formula, we can find magnetic field intensity of different shapes for a straight current carrying conductor. Okay, I hope you understood this video well, this topic well. We'll meet in the next video. Thank you.